Hello world, in this video I'm going to talk about binary exponentiation. So what is it actually? In its most basic form, binary exponentiation is a trick which allows us to calculate a to the power n using only log n multiplications. But it is not just limited to that. It is not just a solution to this particular problem. The technique can be used in various other problems, as we are going to see later in this video. So how do we compute a to the power n? One way is to run a loop n times. So let's call it method 1. This is a very basic method. So what we do is we will assign our answer to be equal to 1, and then we will loop n times. In each loop we will update our answer to be equal to previous answer into a. After that we will end this loop and we will return our answer. This method is fine. The problem with this method is that it is very slow. Say for example, in our case n can be up to 10 to the power 18, and we are assuming a general computer can do about 10 to the power 8 operations in a few seconds. So whatever algorithm we are devising, it should not take more than 10 to the power 8 operations, or it should get completed in less than a few seconds. So here this loop itself going to take n operations, and each operations and n can be up to 10 to the power 18. So this is not a feasible solution for this. Then let's devise some better solution. Let's call this method 2. So what we are going to do is let's take an example, say 3 to the power 180. How are we going to find 3 to the power 180 without doing 180 multiplications? The idea is we should break it in powers of 2 to get a better picture. So 3 to the power 180, if I write 180 in its binary form, to get a better picture of what I wanted to do. So this one is 0, 1, 2, 3, 4, 5, 6, 7. So I can write it in this way, 3 to the power. Now I'm again writing it in decimal form. 2 to the power 7 plus 2 to the power 5 using this, plus 2 to the power 4 plus 2 squared. Now it is again in decimal form. So I can do something like this: 3 to the power 2 to the power 7 into 3 to the power 2 to the power 5 into 3 to the power, I don't need these brackets, let me remove this, 3 to the power 2 to the power 7 into 3 to the power 2 to the power 5 into 3 to the power 2 to the power 4 into 3 to the power 2 to the power 2. So if I somehow know all those powers of 3 which are of the form 2 to the power something, which are actually the powers of 2, this problem is very easy. So any number, say n, if n can be up to 10 to the power 18, any number can be written in its binary form, will not have more than 62 digits, maybe 61 or 62 digits. So if we know somehow all those power till 62, all those 2's power till 62, we can easily solve this problem. So what I mean is, say 3 to the power 2 to the power 0, we know, or we know it is 3. Now how do we calculate 3 to the power 2 to the power 1? That is equal to this into this, the previous one into the previous one. So we have calculated this. Now how do we calculate 3 to the power 2 to the power 2? We will multiply the previous one 2 times. So we have calculated this. Then similarly, we can calculate up to 3 to the power 2 to the power 62 or 3. I think maybe for safe case, we can calculate till 2 to the power 63. 62 will work. We can calculate up to 3 to the power 2 to the power 62 just by multiplying, squaring the previous one. So now we have got this, and now it is very easy. We will decompose every number in its binary form, and we will write and since we know these powers, we will always going to solve this problem. And what is the time complexity of this problem? If you calculate all those 62 digits, then the time complexity would be O of 62. If you have already calculated 62, because we don't need more than these number of instructions. But the problem is this can be improved further. For example, in this case 3 to the power 180, do we actually need all those 62 digits of 2's power to be calculated? No, we only need 0, 1, 2, 3, 4, 5, 6, 7, 8 places. So if we calculated up till 2 to the power 7, we would still be fine. So we will not going to calculate whole 62 things, 62 values. We will just find only values till log base 2n plus 1, which is of the order of log n, or it is also represented as LGN. So this method works very fast. I mean, very fast means this is way too faster than the previous method. So this is the algorithm, and let's go to the implementation. So how are we going to implement that? So let's see how the implementation goes. So this is the code. It is written in C++. So what we have is, let's take an example. A is equal to 3 and B is equal to 180, the same example as before. Let's write B in binary form so that it will be more clear. 1011 0100. So it is 1011 0100. Now we have to do the same thing. Initially A is 3 to the power 2 to the power 0, that is 3. Now in every loop, what we are checking, whether this A is a candidate for our result or not. So what we are essentially doing is, we just check if B and 1, if this position is set, the first position is set, then it will return, then this will return 1, otherwise it will going to return 0. So since here it is not set, so 3 to the power 2 to the power 0 is not our candidate. So we will update this A with 3 to the power 2 to the power 1 by multiplying it 2 times. So now A becomes this, and we will do a right shift 1 bit for B. Why is that? So initially B is 10110100. Now we are going to shift this with 1. If we expand this line, we can get b equals b right shift 1. We can also write b equals b by 2. These are the same thing. So if we shift all those bit to the right, b will going to become 1 0 1 1 0 1 0. Now we are checking if we do b and 1, we have removed this, we are checking this one whether it is a candidate. It means whether 3 to the power 2 to the power 1 is a candidate or not. So in our case it is not, because this position is also 0, so it will not update our result. So result is still 1. Now a is updated, a is again updated. Now a becomes 3 to the power 2 to the power 2, and we have left shift, we have right shift b with 1, so b becomes just these many values. Now again, if b and 1, whether whether 3 to the power 2 to the power 2 is a candidate or not. So yes, it is, because this position is 1. So we update our result to be result into 3 to the power 2 to the power 2. And now we also update a. A becomes now 3 to the power 2 to the power 3. We will also update b. B now becomes just this. So by keep doing that, we will see result will going to become 3 to the power 2 to the power 2 into 3 to the power 2 to the power 4 into 3 to the power 2 to the power 5 into 3 to the power 2 to the power 7. And as soon as it becomes 7, this b will going to reduce to 0, because there will be then no set bit left. So finally when b will going to become 0, this while loop ends, and finally we will going to return our result at that point of time. So result would be this. Yeah, there is another method in which we can do this. So let's see this one, and let's take a smaller example. Say we have to calculate 3 to the power 11, means a is 3 and b is 11. Now what we will do, we will going to do, if b is 0, then return 1, and else we are doing result is equal to power a by 2, a comma b by 2. What we will going to do is, we will change this with a query. Then if I had 3 to the power 5, then I will going to calculate this. Now 3 to the power 5 will again go, if I had 3 to the power 2, then I will going to calculate this. Now this 3 to the power 2 is again going to call 3 to the power 1. If I had 3 to the power 1, then I will going to calculate 3 to the power 2. This 3 to the power 1 will going to say 3 to the power 0. If I had 3 to the power 0, I will going to calculate this 3 to the power 1. Now as soon as it becomes 0, if b is 0, we are returning 1. So this function will return 1 to here. Now here this res is returned 1. Remember, b is 1 actually. So b mod 2 is 1. Then if b mod 2 is 1, we are returning res into a. So 1 into 1 into a is 3, so we are going to return 3. Else we are returning res into res. So for this case we are returning 3 to 3 to the power 2. For 3 to the power 2, we have res equals 3. And since 3 to the power 2 is even, we are just returning res into res. So why for odd we are returning res into a? Say for example, I have to calculate 3 to the power 5. To calculate 3 to the power 5, suppose we have the value of 3 to the power 2. Now what we are going to do, we will going to multiply it twice into 3 to the power 2 and 1 3. Because if we just multiply it twice, it will going to give us 3 to the power 4. We also need to add an extra 3. That is why we are doing this. In even case, let's say this is 3 to the power 4, if we know 3 to the power 2, we don't have to multiply this additional 2 value. So this is the code. I hope you have understand that. Then let's go to the applications. This is my favorite section of this video. Here we will going to apply the technique that we have just learned to solve various problems. The first one is effective computation of large exponents modulo a number. So what it means is now our problem is we have to compute e to the power n modulo some number m. So how are we going to do it? So why do we need this? Because e to the power n can grow very large very fast. Even a 64-bit integer cannot store 2 to the power 64. It cannot store. So if n can grow up to 10 to the power 18, and when a is greater than 2, a is greater than 1, then this number cannot be stored in a int or a long. It will going to overflow. So that is why whenever we are asked to compute an answer which can grow very large, the problem statement generally specifies is to give the answer modulo some number. So how do we going to do about it in our code? So let's open our code. What we will going to do is we'll just replace this res into a to be res into a modulo m. Let's change our argument to add int m. So, and here again we will going to change this a equals a into a modulo m. It is just this simple. Let's move to the next application. Effective computation of Fibonacci numbers. Let me explain you the problem. So Fibonacci number, let's define the sequence. F of 0 is 1, f of 0 is 0, f of 1 is 1, and f of n is f of n minus 1 plus f of n minus 2 when n is greater than 1. So how do we going to calculate nth Fibonacci number? Suppose n is given. Again, one way to do is to run a loop n times. In each loop we keep track of 2 previous variables, and we will update our current value and we will update those 2 previous variables. So this method works when n is small, but say n can go up to 10 to the power 18. What do we do then? That method will not work because this 10 to the power 18 is way too large. So I'm going to use a technique called matrix exponentiation, which I'm not going to explain the principle behind it, but I'm going to explain how it works for this binary, for this Fibonacci numbers. Maybe in some future video I'm going to talk about matrix exponentiation in great detail. So here it is. What I'm doing, I'm writing an equation. Here it is f of n, here it is f of n minus 1, here I'm writing 1 0 1 sorry, 1110, and what we will going to get is okay, we are going to get f of n plus 1 and f of n. You can multiply these two and you will see that we are going to get this. Now how does it help? Say we have uh, say we have here we have f of 1, f of 0, and we want to calculate it, no, we want to calculate f of, we want to calculate f of 2. So we will multiply it with 1 1 1 0, and we will going to get f of 2 f of 1, and we will return this value, whatever this is. Now the beauty is we can suppose we our problem is to calculate f of 3. So what we will do is we will do f of 1 f of 0 into 1 1 1 0 into 1 1 1 0. It will going to give me f of 3 f of 2. Why it will going to give me? Because if we multiply f of 2 into f of 1 with this value 1 1 1 0, you will going to get f of 3 f of 2. So how does it help? Suppose we want to calculate f of n. What do we do then? If we want to calculate f of n, we will just do f of 1 f of 0, and here we will do 1 1 1 0 to the power n minus 1 to get f of n f of n minus 1. Why this works? Because in matrix A times BC is equal to AB times C. I don't know what this property called, but in matrix this works. So it is going to work. And now the beauty of it is, now we don't have to do it n minus 1 times multiply. We can just do the binary exponentiation that we did earlier to calculate very fast how much this number will going to be. Yeah, so this is how we can solve this, and f of 1 and f of 0, we can initialize these values as 1 and 0. So yeah, so it can solve up to 10 to the power 18 and can be up to 10 to the power 18, and it can solve that. So let's move to the next application. Applying a permutation k times. Yeah, this is very interesting. So I have seen a lot of problems in which we have given a permutation. What is a permutation? Say we have given 3 1 2 5 4 as a permutation. What it means actually, suppose our initial numbers are 1 in an array 1 2 3 4 5, and we are given a permutation this. So initially our permutation is 1 2 3 4 5. Now we will change our permutation according to this. Whatever is in the third place will going to go to the first place. So p of 1 will going to become whatever is in the third place will going to go to the first place. So it is 3. Whatever is in the first place will going to go to the second place. So it will going to 3, 1, then 2, then 5, then 4. Now how do we calculate second permutation? So the same thing, whatever that will going to go to the third place, whatever that was previously in third place will going to go to the first place. So here in this case it is 2. Whatever that was previously in first place will go to the second place. So it is 3. Whatever was in second place will go to third place. It will going to be 1. Whatever was then in fifth place, so it will be it will be 4 and it will be 5. Now what can we see here actually? And suppose our problem is what is the final permutation after k times permuting this? Means what is the kth permutation? What is the sequence of kth permutation? And k can be up to 10. So if k can be up to 10, we can just directly do this permutations and say n can be up to 10 to the power 5. If k can be up to 10 to the power 10, in each permutation we have to check 10 times. In each permutation we have to make a new permutation, we have to run all those array. That means it is about 10 to the power 5 and the total number of permutation we want is 10. We have to do it 10 times. But the problem is, what if k goes to 10 to the power 18? It can be any value between 1 and 10 to the power 18. Now it is impossible to solve it with this method. So as usual, binary exponentiation came to our rescue, and this is a very powerful tool. This is a very interesting fact about binary exponentiation. I liked it a lot because why do we have to compute this permutation every time? Say we have P0. I have already given P0. Say we compute P1, which is the permutation. Say using P1, I can compute P2, right? Yeah. Now, we will not going to compute P3. We will going to compute P4. Why? And how do we do this? Since we know the permutation P2, we will apply P2 to our initial permutation, whatever it is. So we will get P4. Similarly, we will get P8. And we will go till P2 to the power 64, 63 or 64, whatever values. And we will again, the beauty of this is we will again do the same thing. Like if k is say 10 to the power 18 or something, k is more than equal to 10 to the power 18, we will divide k in its binary form. So 1 1 0 1, say k is this number, this is actually 13. So what we do is, we know 2 to the power 3, we know 2 to the power 2, we know 2 to the power 0. So what we have to do is, we will only going to apply these 3 permutation on our initial number. We will only have to apply this P1, this P4 and this P8. So I think it is clear to you that how are we going to solve this. So in our initial permutation we are going to apply these 3 so to get our final answer. And what is the time complexity of it? The time complexity is O of n log k. So yeah, this is this method, but there is even a faster method of it can be done in O of n simply. Uh, I'm not going to talk about that method in detail because it is beyond the scope of this video. I'm just going to give you a hint. Uh, so, so actually what we will do is we will make a graph of this permutation, and what our graph yield, it will always going to yield uh, all those nodes will be in cycle, and we have to tackle each cycle independently. Uh, so in this way we can find what the solution is, what will be our final permutation is O of n. So let's move on. Uh, the next application is number of path of length k in a graph. So this is also, I think, beyond the scope here, but I'm just going to give you a crux of it. It is like, it is the same thing. Means we will be given a matrix and we have to compute it k times, and k can go up to very large. I will talk about this when I'm discussing graph. So this is it. The next application is variation of binary exponentiation, multiplying two numbers modulo m. Okay, now this is very interesting. So let me talk about this. So what we are given, so let me frame another problem. What we are given is, say, a to the power b, a to the power. So we are given a to the power b mod c. What is creating problem is c, because let's say c take a value of, c can be up to 10 to the power 12, and let's say c takes a value, c equals 10 to the power 12. What problem it will going to create? Let's see the code. So here let's call it m, not c. I'm sorry about that. So let's call it n, and m is equal to 10 to the power 12. So what it is going to do here is, now res can be up to 0 to 10 to the power 12 minus 1. Means it is of the, can be of the order 10 to the power 12, and a is a very large number. A can be up to 10 to the power 12. So a can be of the order, a can be of the order 10 to the power 12, because we are moduling it with 12. So it is just, it can be just smaller than these values. So what is the problem here? Res into a will overflow. If say both of these values are, say, 10 to the power 11 and 10 to the power 11, res and a, then res into a will going to overflow. If you get what I am saying, then very good. So how do we going to deal this solution? How do we going to deal this problem? I haven't. So we will just give up and we will continue. Or what we can do is to modify this multiply operation. We will not directly multiply these two numbers here and here. These are the root cause of overflowing. So what we will do is we will write another multiplication function which is same as this power function, and we will, instead of multiplying it directly here, we will call that multiplication function. So res will going to become, instead of this, res will going to become, let's call it mult res comma a comma, let me erase all of this. So let me erase. So what are we going to do is we will not write it in this way. We will write another separate multiplicative function which will take res, which will take a, and which will take, say we have long m, it will take m. Similarly here we will do the same thing. It will be mult, it will take a, it will take a, it will take m. So what mult will do? Mult will do the same thing what we this power is doing. Instead of multiplying here, we will going to add, and add will not going to overflow, because even if we are adding two numbers which are 10 to the power 12, we will get a number which is 2 into 10 to the power 12, which is way beyond 10 to the power 18. So this task is for you. You will write your own multiplication function, and you can comment it that in the bottom. So that's it. And I think all those applications are covered. Let's move on to the bonus section. In this section, I'm going to tell you a very cool yet very useful trick which can be applied to solve many different problems. Let me just frame a problem. Suppose we have to calculate f of a to the power f of b, where fa is the 8th Fibonacci number modulo some prime p. Now how do we going to do this? One thing to notice is f of a can grow very large very fast. Similarly f of b. So it is impossible to calculate, say a is about 10 to the power 18. It is impossible to calculate this number, to store this number in an int. So what most beginners generally do is they calculate x, which is equal to f of a mod p. They calculate y, which is equal to f of b mod p. And now to find this, they calculate x to the power y mod p. But this method is wrong actually. So this method will not work. Let me take an example and understand why this method will not work. Let's say we have to calculate f of 4 to the power f of 6 mod some prime number p. Let's say p is 7. So f of 4 is actually 3 and f of 6 is actually 8. Let me write the sequence: 0, 1, 1, 2, 3, 5, 8. So this is f of 4 and this is f of 6. So when we calculate x equals f of 4 mod 7, that means 3 mod 7, which is equal to 3. Y equals f of 6 mod 7, that is 8 mod 7, which is equal to 1. Now we calculate x to the power y mod 7, which is 3 to the power 1 mod 7, which is actually 3. So this method give us answer 3. But what is the actual answer? Let's see. So we have f of 4 to the power f of 6, means 3 to the power 8. This number turns out to be 6561. Yeah. So if we calculate this number modulo 7, we will going to get 2 as a remainder. So, and 2 is not obviously equal to 3. So why is this method not working? It is because because our method is wrong. So what we have to do is we will calculate f of a, we will calculate x as f of a mod p, but for y we have to calculate it f of b mod p minus 1. Now this will going to work. So why this will going to work? I will talk more about it is based on Euler-Totient function, because the totient of p is p minus 1. So when p is prime, so it works here, and I will maybe in some other video I will going to talk about this in more detail. So let's see if it works in this problem or not. So similarly, so here x is f of a mod p means 3 mod 7, that is 3. Y is f of b mod p minus 1, that means 8 mod 6, that is 2. Now we will going to calculate x to the power y means 3 to the power 2 mod 7, which is 9 mod 7, that is equal to 2. So it works. So that's it for the bonus part, and thank you for watching this video. Bye. And one more thing that I wanted to talk is, it is not that only it works in only Fibonacci numbers. Let's say we have a to the power b to the power c mod p, where p is of course prime. We will calculate a mod p, and then we will calculate b to the power c mod p minus 1. We already know how do we calculate this, and it is not limited to these two. It can be extended. Say we have a to the power n factorial mod p. So we will going to calculate a mod p and n factorial mod p minus 1. So you get what I'm trying to say is, whenever we had an exponent which is very large, so we have to calculate it in modulo p minus 1, and it will work. Okay then, thanks for watching this video. Bye.